Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Everyone, it's my great pleasure to introduce Nina Balkan, who's a professor at Georgia Tech. She did her PhD under Avrim Blum at CMU, and so Nina's work, Nina moves seamlessly between machine learning, algorithms, game theory, and she's going to tell us very interesting things about clustering, which has wide applications. So, Nina.
All right, thanks. Great, so I'll talk about finding low-error clusterings, and in fact, an even better title for this work is Approximate Clustering over the Approximation, and the meaning of this title will become clear later in the talk. And this is, yes, and this is a line of work joined with a number of people that I'm going to describe throughout the talk. All right, so this talk is about unsupervised learning or clustering, which is as you probably all know, it's a major research topic in both algorithms and machine learning these days. Why? Because problems of clustering data come up everywhere in many real-world applications. And a few examples of such applications include clustering news articles or web pages by topic, clustering protein sequences by function, or, say, clustering images by who is in them. Okay? Now, many of these clustering problems can be formally modeled as follows. So we assume that we are given a set S of n objects, say, n documents, and we'll assume that there exists some unknown, correct, desired target clustering. So that means that each object has some unknown true label, in this case, the topic. And then in this context, our goal would be to find a clustering of low error, where the error of a given clustering C prime is defined as a fraction of the points that are misclassified with respect to the target clustering up to the indexing of the clusters. Right, so again, the setup here is as follows. We assume that we have a target clustering, C, which is a partition C1, C2, Ck of the whole set of points. And now if we are given a new clustering, a clustering C prime, which is another partition C1 prime, C2 prime, Ck prime, of the same set of points, then we define the error of C prime with respect to C as a fraction of the points that you get wrong in the optimal matching between the clusters in C and clusters in C prime. Okay, that's a natural notion of error rate. It's the analog, in the context of clustering, is really the analog of the 0-1 loss in the context of supervised classification. So it's a very natural notion of error rate, since in the context of clustering, we don't really care about the getting the names of the clusters right. We only care about getting the clusters themselves right.
But let's say if I start calling them fashion and sports, other way around.
You don't get penalized, which is, so we only care about getting the clusters right, not the names right. And this notion of error rate exactly captures that. Because so the error is defined, it's the fraction of the points that you get wrong in the optimal matching between the clusters.
But how does this formula captures? You need to know the sigma.
No, it's minimum. It's minimum overall possible permutations of the labels. It exactly captures what you wanted to capture. All right, so that's a natural goal in the context of clustering. One can argue that, to get a clustering of low error according to this notion of error. I'm not claiming that it's the only notion of error that you can consider, but it's definitely a natural one. Okay, so that's our goal, to get a clustering of low error. Now, in order to do so, as it is usual in a clustering setting, we assume that we are given a pairwise measure between pairs of points, so a measure of similarity or dissimilarity between pairs of points. So for instance, in the document clustering case, this can be something based on the number of keywords in common, or in the protein clustering case, this can be something based on the edit distance, and so on. And now, clearly, since our goal is to get a clustering of low error, this pairwise measure has to somehow be related to what we are trying to do, has to somehow be related to the topicness, because otherwise there will be absolutely no hope to do anything. Okay, and for the rest of my presentation, I'm going to focus on the case when the pairwise measure that we are given is a is a dissimilarity measure, and in particular is a distance function, satisfies the triangle inequality. All right, so that's our problem. Now, a classic approach to solve such a problem especially in the theoretical computer science community, also in machine learning sometimes, is to view the data points as nodes in a weighted graph, where the weights are based on the distance function that we are given, and then to pick some objective function to optimize, like k-median, k-means, mean sum, and so on. And just to remind you, or in case you have never seen it, so in the k-median clustering problem, the goal is to find the partition C1 prime, C2 prime, CK prime, and center points or medians for these parts, for these clusters, in order to minimize the sum over all points of the distance to their corresponding median. So that's the k-median clustering objective. And in the k-means clustering case, the goal is to minimize the sum of the squared distances, while in the mean sum clustering case, the goal is to minimize the sum of the intra-cluster dissimilarities. All right, so again, a standard approach to solve such clustering problems in the theoretical computer science community, and also in machine learning, is to view the data points as node in a weighted graph, where the weights are based on the dissimilarity function that we are given, and then to pick some objective to optimize, and then to develop algorithms or approximation algorithms for these objectives. So I should say that many of these objectives are actually NP hard to optimize, and so the best you can hope to do is to design an approximation algorithm for them. And significant effort has been spent in the last few years on developing better approximation algorithms for many of these objectives, as well as developing better in-approximability results for them. So significant effort has been spent on this. For example, the best known approximation algorithm for k-median is a 3 plus epsilon approximation, and it's also known that it's NP hard, beating 1 plus 2 over E is NP hard. And actually, this is a result that appears in a paper by Kamal, right, Mohammad Mahadian, and Amin Saberi. Okay, so this is all right. I mean, this effort is all is justified sometimes. However, in the clustering problems that I was talking about, our goal is to get a clustering of low error. Our goal is to get the points right, to get close to the target clustering. And so that means that in those problems, if we end up using a C-approximation algorithm for objective phi, say to k-median, in order to minimize the error rate, in order to, say, cluster our document, then that means that we must make an implicit assumption that all the clusterings that are within a factor of C of the optimal solution for our objective phi are, in fact, close to our target clustering. I mean, it's implicit, because otherwise the clustering that we output will not going to be meaningful. So again, if we end up using a C-approximation algorithm to objective phi, say to k-median to cluster documents, where what we really want to do is to get a clustering of low error, to get close to our target clustering, that means that we must implicitly assume that any clustering that is within a factor of C of the optimal solution for objective phi must in fact be epsilon-close according to the symmetric difference distance to our target clustering. So it's a parameter. It's closeness to the, it's how close we are to the target clustering.
I have a basic question about your objective function. Given a clustering,
yeah.
how do you know how close it is to that?
So we have this notion, that's why we introduced the notion of distance between two clusterings. So,
but I don't know the ground truth.
Right, that's why the problem is difficult, and that's why people go and come up with surrogate objectives. Right, exactly, because it's difficult to think I don't know the ground truth. It's given my, what I have, my similarity information, I cannot compute distance to the ground truth, and so that's why people look at these surrogate objectives, like proxy objectives, like let's say k-median is something that I can measure. Actually, that's one of the reasons for which people develop approximation algorithms for clustering. But the point that we make is that what we really care is to get close to the target clustering, and then the question is, under what conditions can we get close to the target clustering?
Are you saying that there exists an epsilon? So for every C there exists an epsilon that is like low enough?
No.
It's a definition, I guess.
So it's an assumption. So okay, well, so it's an assumption. Okay, so I'm not. I'm okay. Let me call this a C-Epsilon property, which says my instance satisfies the C-Epsilon property if any clustering that is unifactor of C of the optimal solution is epsilon close to target clustering. It's an assumption that might be or might not be satisfied, but the claim is that I guess no, it's not the claim, it's more like the motivation here is that if you use a C-approximation algorithm for objective phi, it must be the case that something like this should be satisfied for a reasonably small epsilon, because otherwise the clustering that you are going to output, your C-approximation, is going to be far from the target clustering anyway, so it's not going to be meaningless. It's going to be meaningless. It's not, okay, so what I'm going to show is that we're going to be able to cluster well under such an assumption.
If I understand well, you can choose different phis, and you say that the phi is a good choice, like let's say the k-median is a good choice if it gives you back the clustering, and this is the c-epsilon property. Okay.
Okay, so think about it as being an assumption, and I'll go through some of the theorems, and then we'll see how to interpret it. So for now, it's an assumption. So I'm going to say that my instance, what's my instance, is a similarity function that distance function that I'm given, and a hidden target clustering that I don't know. So that's my instance, that's the input to my algorithm, and I'm going to say that my algorithm is going to satisfy this, my instance is going to satisfy this property if it is a case that for my instance, all the clusterings that are within a factor of C of the optimal solution for phi are close to the target clustering. So it's a property of a given instance. And the type of guarantees that we're going to make is that if this property is satisfied, then we're able to cluster well.
So my question is mostly like, how truthful is that assumption? Of course it's trivial with epsilon equal to 1 if you normalize.
Exactly.
But how truthful is it to expect that this is the case for epsilon?
Okay, so I'll comment on that a bit later.
That was my question.
Okay, so there is a question. So I'll comment on that later, okay? But for now, the motivation is that I'm trying to give is that if this is not satisfied anyway, using approximation algorithms to cluster well, it's not a good idea. So let's assume that this property is satisfied, and let's see what we can do with it. Okay, so given the C-epsilon property, so what we can show, first of all, we can show that under the C-epsilon property, the problem of finding a C-approximation to objective phi is as hard as it is in the general case. So the problem of finding a C-approximation for objective phi does not become easier. However, under this property, we are able to cluster well. We show that we will be able to cluster well. We'll be able to get close to the target clustering without approximating the objective at all. So we solved the problem that we really wanted to solve without ever approximating the proxy objective at all. And that's why we call this actually approximate clustering or the approximation. And please ask again your question, Alexandra, later, because I have answers to it. But it's too early to give them now. Okay, so in particular, what we can show is that, so here's an example of a result. We can show that for the k-median clustering problem, for any c strictly greater than 1, under the C-epsilon property, we'll be able to get order of epsilon close to the target clustering. So we will be able to output a clustering of low error. And we are able to do so even for values of C, or getting a C approximation to the k-median clustering objective is actually NP hard. And moreover, if the target clusters are sufficiently large, we're able to get even epsilon close to the target clustering, which is in some sense the best we can hope to do.
So you mean epsilon versus order epsilon?
Yeah, so this is actually order of epsilon over C minus 1. So I'm hiding some factors here, right? So if the target clusters are sufficiently large, you can get exactly epsilon close, which given the assumption is really the best you can hope to do.
So in the hard cases, you would get close to the right cluster, but then it would be hard to find the median.
Right, so what we end up doing is we'll output a clustering that is close to the target clustering, but we have no guarantee, we do not necessarily have a small k-median objective value. So that's why we do approximate clustering in some sense without the approximation.
This assumption seems almost identical to the implementers model. If you can't fix it, it ain't broke.
Again? I'm sorry?
The implement model. If we can't fix it, it ain't broke. This sounds very similar to this assumption. Do you have any reason to believe in the assumption, the C-epsilon property?
No, okay, so no, I have no reason to believe on this. There are multiple answers, actually. One of them is, actually we did, so let me go through the result. I'll come back in a second again. So, okay, let me comment on this again later. Okay, but that's a very good question. So is this assumption ever satisfied? And again, I'm going to comment on this later. All right, so now let me make before actually presenting some of our main results, let me make a note from let me just make a quick note. So now from an approximation algorithm's perspective, a natural and absolutely, totally legitimate and natural motivation for trying to improve our approximation ratio from C1 to C2, where C2 is strictly smaller than C1, is that maybe the data satisfies this condition for C2, but not for C1. And this is absolutely natural and legitimate because, in fact, we can even show instances. So for any C2 smaller than C1, we can construct instances that have the property that they satisfy the C2 epsilon property, but do not satisfy even the C1 0.49 property. Okay, so this is an absolutely natural. So it's absolutely natural. Yes?
Do you think another assumption could be just having a softer version of the assumption, where instead of requiring that all clustering satisfies some fraction of them satisfies?
Okay, so please bear with me for a second. I have at the end actually, so I have multiple answers for the three questions that I got, but are about the same topic. So I find this assumption cool from a theoretical point of view because we get around in approximability results by using implicit assumptions that are made, implicit anyway. I'm not promoting it as something that, I'm not saying that this is satisfied in the real world, although we do have some experimental evidence for it. And actually what I really think we should, and I comment on that, so I'm going to have a whole part of the talk where I'm going to talk more broadly, but it may be more interesting to consider more broader properties. But I find this as a concrete, cool assumption from a theoretical perspective.
Maybe you can do the question.
So if it's along the same lines, please wait. Okay.
It's not exactly along the same lines, though. Like, I don't understand what you saw about the objective phi, because if phi is actually the distance, so if phi were to be equal to the distance between the clusters, the definition you had at the beginning, then what does that mean?
So this assumption, so here we assume, so it's an assumption about how the distances and closeness to the truth relate. The distances, objective phi, the value of the objective phi and closeness to the truth. Yes, it's an assumption, but not all the instances are going to satisfy this assumption, but the type of guarantees that we make is that if this assumption is satisfied, then we'll be able to cluster well.
The assumption is for specific objective function.
Right,
yeah.
Exactly. It's not a generic assumption. So it's an assumption, yeah? Okay, good. So just a quick comment before I guess I move on to some concrete results, and then this will hopefully clarify some of the questions. So the comment was that from an approximation algorithm's perspective, an absolutely legitimate and natural motivation for trying to improve the approximation ratio from, say, C1 to C2, or C2 is strictly smaller than C1, is that maybe our data satisfies the C2 epsilon property, but not even the C1 0.49 property. Okay, and this is absolutely legitimate. We can show such data sets. However, with the kind of the very nice and interesting fact is that in our work we can do much better. We are able to cluster well, even for values of C, or getting a C approximation to the objective phi is actually NP hard. So that's an interesting fact. All right, and let me now give examples of results and what we can show on this framework. So for instance, so here is an example of a result. So we can show that if for the k-median clustering objective, yeah, if the data satisfies the C-Epsilon property, then we can get order of epsilon over C minus 1 close to the target clustering. And moreover, if the target clusters are sufficiently large, we can even get epsilon close to the target clustering. Or the notion of large also depends on C.
So does the algorithm, it needs this C and epsilon?
It does, yeah. So it needs, or, yeah. So
you could do some kind of binary search.
It's not clear because, again, you need to be careful because, again, you cannot test. If I give you a clustering, a proposed clustering, you cannot test how close it is to the target clustering because you don't know the target clustering. So it's not, you cannot quite do binary search. So you need to be more careful and to consider the parameters in a search.
Size here is cardinality of the target clusters, right?
Yes. Okay, and so we can do something similar for the for the k-means clustering objective, and this is based on these results appear in the original paper, and we also looked at the mean sum clustering objective, And so here we show, again, if the data satisfies the C-epsilon property, and if the target clusters are sufficiently large, then we can get order of epsilon over C-1 close to the target clustering. Now, in the case of arbitrary small target clusters, if the number of clusters is smaller than log n over log n, then we again can get order of epsilon over C-1 close to the target. However, if k is larger than log n over log n, then what we do, we output a list of size, a small list, such that the target clustering is close to one of the clusterings in the list. And this is actually a joint work with Mark Braverman. So these are examples of results. And I should also...
K is the number of clusters?
The number of target clusters.
It's known? It's fixed? It's
Yes. Yes. It's part of the input. Okay, so these are examples of positive theoretical results, and I should also point out that in a recent UI paper, actually, we implemented the algorithm for large clusters for the K-median objective, and it turns out that this algorithm, or variant of this algorithm, provides state-of-the-art results for protein clustering. Okay, so this algorithm seems to be useful. So in other words, this is a standard data set where definitely the assumption is satisfied. Now, obviously, we're not going to be satisfied on lots of data sets necessarily. Okay, and I hope that this provides a partial answer to your question, and I have an even more complete answer at the end of my presentation, once I go through this C-epsilon property. All right, so this is an overview of the type of results that I'm going to talk about. And for the rest of my presentation, I'm going to pick an objective, in particular the K-median clustering objective, and I'm going to show how we can cluster well if the C-epsilon property is satisfied. Right, so let's assume that indeed, for our given data set, the C-epsilon property is satisfied. That means any C-approximation to the K-median optimal solution is, in fact, close to the target cluster. Okay, and just to simplify things, let's assume that this is just to avoid technicalities. Let's assume that the target clustering is a K-median optimal solution and that all the clusters are large enough. So they have size at least 2 times epsilon times n. This is, again, just to avoid technicalities in the presentation. We don't need these assumptions in general. Okay, now, let's introduce some notation. So for any point x, let's denote by w of x the distance to its own center. And let's denote by w2 of x the distance to its second closest center. And so that means, and let's moreover denote by W average, the average over all points x of W of x. And so that means that just by definition, opt will be n times W average. You see the value of the optimal K-median solution, right, which by my assumption is also the target clustering. Okay, so this is just some notation. Now, let me describe two properties, two implications that we can derive. So the first one is an implication of the C-epsilon property, and it says that if the C-epsilon property is true, then we can show that at most epsilon times n points can have W2 smaller than C-1 W average over epsilon. Okay. Why? Because otherwise, if more than epsilon n points have W2 small, then what we could do, we could move those points to their second closest cluster, and we would do so without increasing the objective by more than C-1 W average over epsilon times epsilon n, but is C-1 times opt, and so you get a clustering that is still a C-approximation to the K-median optimal solution, but which is now epsilon far from the target clustering. So the C-epsilon property will be contradicted. Okay, so a consequence of the C-epsilon property is that we have it at most epsilon times n points can have W2 smaller than C-1 W average over epsilon. Now, an even simpler fact to prove is that at most 5 epsilon n over C-1 points can have W greater than C-1 W average over 5 epsilon. And this just follows the Markov inequality, so it's very easy to show. And so that means that now that for the rest of the points, for what we call the good points, we have a huge gap. So for the rest of the points, we have that W of x is smaller than C minus 1 W average over 5 epsilon, and W2 of x is greater than C minus 1 W average over epsilon. So for the rest of the points, we have a huge gap. So W is smaller than C minus 1 W average over 5 epsilon, and W2 is greater than 5 times this quantity over here. Okay, so let's now denote this quantity by D. Let me call this quantity D critical. And so what we have is that most of the points, what we call the good points, or 1 minus order epsilon fraction of the points, look like this. So they are within distance D critical of their own center. And so that means that by triangle inequality, we get that any two good points in the same cluster will be within distance 2 times the critical of each other. Now, we also know that any good point is a distance at least 5 times the critical to any other center. And so again, by triangle inequality, this then implies that the distance between any two good points into different clusters is at least 4 times the critical. And so now that means that if we now define a new graph G, or we connect two points x and y, if they are within distance 2 times the critical of each other, then what we get is that the good points in the same clusters are going to form a clique. So they're going to be connected in that graph G. And we also have that good points into different clusters do not even have a neighbor in common in this graph G, because we know that two good points in two different clusters are a distance at least 4 times the critical of each other. And so that means that now basically the world will look like this. So the good points are going to form cliques. So in the graph G, so in these are the good sets depicted over here. Now good points might connect to bad points, and bad points might connect to bad points. However, any bad point will only going to connect to a good set, because we know that any two good points into different sets are at distance at least 4 times the critical of each other. Okay, so the world in the basically looks like this. So good points form cliques. They connect to bad points. Bad points can connect to bad points. However, any bad point can only connect to a good set. And so now that means that if we furthermore assume that the clusters are large, in particular if we assume that the clusters have size at least 2 times the size of the bad set, roughly, then what we can do, we can create a new graph H, where we connect 2 points x and y if they share enough neighbors in common in the graph G. And then in this new graph, so the components of H, the k largest connected components of H, are going to split like this, and we can just output this clustering, and this will be a clustering of low error. In particular, the error that we get will be basically order of the fraction of the bad points. Because we know that any connected component of H is going to correspond to a good set plus possibly some bad points. So we correctly cluster all the good points, might make mistakes on the bad points, but it's a small fraction of the whole set of points. So the error rate that we get is order of epsilon over C minus 1. Okay, so that's basically the algorithm for the large clusters case.
So just a quick question. Are the bad points the ones that are currently labeled incorrectly, or the ones that don't fit the sort of separation assumption?
Right, so the bad points are defined by the, are defined in the analysis, right? So are those points that do not satisfy the property that they are much closer to their own center than to any other center. So the bad points are defined in the analysis. Okay, now if the target classes are not so large, so basically, so the previous algorithm that I described doesn't really work. Because why? Because we could have some classes that are completely dominated by bad points. However, luckily, it turns out that some algorithm that is equally simple, we're going to do the right thing. Okay, and what's the algorithm? So what we do, we just as before, we construct the graph G, where we connect 2 points if they are within distance 2 times the critical of each other. Then what we do, we just pick the vertex of the highest degree in the graph G. We pull out its entire neighborhood, and we just repeat. Again, pick the vertex of the highest degree in G, pull out its entire neighborhood, and repeat. And now what we can show is that this algorithm gives us a clustering of small error rate. And the main idea here is to basically charge off the errors to the bad points. Okay, and how? So basically, here is the analysis. If the vertex v that we picked, the vertex of the highest degree v that we picked, was a good point, then we are happy because we know that we'll pull out an entire neighborhood, an entire good neighborhood. Yeah, so that's a good case. However, if the vertex v that we picked was a bad point, like this one here, then we might end up pulling only part of a good set. Okay, so and we might end up missing, say, Ri good points over here. However, since we are greedy, we know that we must have pulled out at least Ri bad points as well. This was the vertex of the highest degree, and so if we missed Ri points here, that means that we must have pulled Ri bad points here. And so that means that we can basically charge off all the errors to the bad points. And so we get a clustering of error again, order of the fraction of the bad points. And notice that here it was essential to use the fact that any bad point only touches one of the good sets. So this case was the only bad case that we have to consider.
So in this picture it will be two clusters, it will be partitioned into two clusters. The original cluster.
Yes, but the point is that this will not, so that's true, right? So what we end up, so if you pick a bad point here, we might end up only pulling part of a good set plus a bad set. So we might miss some good points. But the claim is that overall, if we sum over all target clusters, we're not going to miss too many good points because since we're greedy here, the size, so if we missed Ri good points here, we might pull out at least as many bad points. And so that means that we always can charge off such errors to the bad points. Right, so. And so that means that basically overall we get a clustering of low error. Okay, now going back to the large clusters case, it turns out that we can do even better. So we can get even epsilon close to the target clustering if the target classes are large. But now the notion of largeness will going to depend on this parameter c. Okay, and what's the main idea? The main idea is that there are really two kinds of bad points. So epsilon n bad points are confused bad points in the sense that their distance to their second closest center is not too much larger than the distance to their own center. So these are confused points. Now the rest of the points, the rest of the bad points are not really confused. They have W2 much larger, larger than C minus 1 W average over epsilon than W. However, they are far from their own center. So these are the non-confused bad points. And it turns out that, it's kind of nice. You can recover the non-confused bad points. And in particular, what's the algorithm, given the output, given the clustering C prime from the algorithm so far, what we do is just reclassify each point x into the cluster of the lowest median distance. Okay, so we just have a post-processing step. And now the idea is that, why is this giving us a clustering over almost epsilon? The idea is that the non-confused bad points have a huge gap, at least 5 times the critical, from the distance to their own center and the distance to any other center. Now, of course, we don't really know which these centers are, but remember that any good point is within distance d critical of its own center. And so combining these two facts, you get that the non-confused bad points are much closer to good points in their own cluster than to good points in any other cluster. And now if these clusters are large enough, then the median will be controlled by good points. And so the non-confused bad points are going to be pulled out in the right direction. So we're going to reclassify them correctly.
So, but you don't compute the median. Do you compute the median?
Yeah, so given the clustering so far, for each point x, we compute the median distance to each of the clusters and reassign it to one of the smallest median distance. So it's a post-processing step. And if you do so for the large clusters case, this gives you a clustering of small error.
What do you compute exactly?
The median. By median, I mean like the statistical median.
The statistical median actually.
Yes.
Because the word median is used.
Yeah.
Census here.
No, statistical median. All right, and now a number of technical issues. So in particular, so the definition of the algorithm, so the description of the algorithm that I had so far depends on this value d critical, which is c minus 1 W average over 5 epsilon, which depends on W average, which in turn depends on knowing knowing opt, which is the value of the optimal solution, say, for the k-median. And now, of course, we don't really know what that is. Okay, now, how can we do this? In the large clusters case, so what we can do is the following. So we can start with a log S of W, and we can keep increasing it until we get to a point where the k largest components of the graph H are large enough and cover a large fraction of the whole set of points. And we can show that if we do so, then we do get a clustering of low error. And at a high level, the idea is as follows. So if we do reach the right value of W, so we keep increasing this value of W, and when we on output, so for the clustering that we output, if we do reach the right value of W, then we clearly get a clustering of low error, because I just argued that. Now, however, we can, our guess might be too small, so we might stop earlier. But because we make sure that all the components that we output have, are large enough, have size at least, say, the size of the bed set, this then ensures that all the components of the graph H correspond to different good sets. And this, together with the fact that we only output clusterings that cover a large fraction of the space, implies that the clustering that we output has a small error rate. And in order to show this, we basically use the structure of these graphs H and W, and in particular H and G and H, and in particular we use the fact that for smaller values of W, these graphs are only sparser. Okay, so that's the high-level idea. Yes?
So if I remember correctly, the algorithm only depended on epsilon and c through d critical, right?
It depends on epsilon and c, which we assume that, right, so these are parameters, but it also depends on W average, which is opt over n. So,
the question is there dependence on epsilon and c besides
through d?
Besides through the d critical, also b, like it's also on. So the original algorithm, okay, you mean no. So the other one, well, yeah.
So
No.
in that case, why you need to know c and epsilon?
So the algorithm is independent of c-epsilon. You have a good way of finding d critical. So that's an important property for the algorithm, that you don't need to know what the assumption is exactly.
Well, you mean practically speaking, yes. And I guess this is what my student Coffer does when he implements the algorithm, right? So he comes up with reasonable guesses of the critical, right? But theoretically speaking, right, so this depends technically on epsilon and c, and moreover also on W average, which is opt over n. And so again, and we don't really know opt, but luckily it turns out that in the large clusters case, we can kind of implement a variant of this algorithm where we keep increasing the value of W until the clustering, the k largest connected components of H cover a large fraction of the space and are large enough. And we then use the structure of our problem in order to argue that this way you get a clustering of low error. But this trick only works in the case where we have large clusters. And
What was B again?
Is the number of bed points. I guess B is the fraction of bed points. So this should really be B times n. B is a fraction of bed points.
Because it's c minus 1 by...
What's exactly the right? So basically, okay, we are asking what's the exact quantity. Let me quickly take a look. Oops. Right, epsilon over c minus 1 times n. Yeah. Okay, now in the small clusters case, however, the trick that I had on the previous slide doesn't really work. What we have to do in this case is to actually to first use the constant factor approximation algorithm for k-median, and then use that approximation in our algorithm, and then the approximation factor only goes into the final error guarantee. But actually, it's an interesting, cute technical question to see if in the small clusters case, we can get rid of really running an approximation algorithm first. Okay, and I should also say that we have also looked at an inductive version of this. So we also analyze an inductive setting where we assume that the set of points that we see is only a small random sample from a much larger abstract instance space, and our goal is to come up with a clustering of the whole instance space. And so algorithmically, what we do in this case, we first draw a sample S, we apply our algorithm on the sample, and then we insert new points into our clusters as they arrive. And so what we really do, basically, we first run the algorithm on the sample. So in other words, for example, for the large clusters case, we create the graph G, the graph H. We take the largest component of H. And then when new points arrive, we insert them based on the median distance to the clusters produced over the sample. And then we can argue that this gives us a clustering of low error. And in particular, the key idea here is that the key property that we use in order to argue correctness for the large clusters case is that in each cluster, we have more good points than bad points. This is what we needed in the case where we knew the value of W, or if we don't really know the value of W, we needed that we have twice more good points than bad points. Now, however, if the clusters are large enough, and if the sample itself is large enough, this will also going to be true over the sample as well, and so this helps us to argue correctness overall. Okay, so we also looked at an inductive version of this algorithm. I should also, let me just mention that we also looked at k-means and mean sum. For k-means, a similar argument, we can just derive a similar argument as for the k-median clustering objective. For mean sum, however, the argument is a bit more involved. The algorithm is equally simple. So the first solution that we had to deal with mean sum was to connect it in a standard way with something called the balanced k-median objective, where the goal is to find a partition and center points in order to minimize this quantity, which is the sum over all points of the distance to their corresponding clusters times the size of the cluster they are in. Okay, and it turns out that for this balanced k-median, we can derive similar properties as for mean sum, so for this balanced k-median, we can derive similar properties for k-median. However, the main difference is that in this case, we don't really have a uniformly critical. So it turns out that here we can have large clusters with lots of points that are very concentrated with a small diameter, and we could have small clusters with very few points that have a very huge diameter. But luckily, it turns out that a similar argument can be applied in this case as well if we are careful and extract first the large clusters, and then second largest, and so on. And this gives a way to deal with the large clusters case for mean sum or balanced k-median if C is strictly greater than 2. And in order to deal with the small clusters case, we had to do a much more refined argument. We had to go for a more refined argument. All right, and so to summarize this part of the talk, this part of the presentation, so let me go a little bit of a high level. So one can think, one can maybe view the usual approximation algorithm approach to clustering as saying we cannot really measure what we wanted. That means closest to the ground truth, because it goes back to your comment. So we cannot really measure what we want closest to the ground truth. So let's set up a proxy objective that we can optimize, and let's approximate that. Okay, so this is one way to think about the usual approximation algorithm's approach to clustering. Yeah, so this is almost like in this picture right here. So this guy is about to jump off the building, and we tell him we couldn't get a psychiatrist, but perhaps you'd like to talk about your skin. Dr. Perry here is a dermatologist. Yeah? So one could interpret the usual approximation algorithm's approach to clustering as exactly this way. Okay? However, this is maybe perhaps a bit too cynical, because the point is that if we end up using a C-approximation algorithm to cluster our documents, that means that we must make an implicit assumption about how distances and the closeness to the ground truth relate. So we must make an implicit assumption about the structure of our problem. And so what we do in our work, we make it explicit. And if we make it explicit, we get around in approximability results by using the structure that is implied by assumptions that we are making implicit anyway. Okay, so this is one way to think about this work. And I think it's kind of cool, from a conceptual point of view and from a theoretical point of view. Now, of course, I don't say that this assumption is an assumption that will be satisfied in practice. And in fact, what I say is that we should really analyze other interesting properties, other ways in which the similarity or the dissimilarity information relates to the target clustering. Okay, and actually, let me just make a comment that it will be also interesting it will be interesting to also use this framework in order to apply to other problems where the standard objective is just a proxy and maybe where implicit assumptions could be exploited to go around inapproximability results. So it would be nice to apply this framework to other problems as well. And just as a comment, recently I have been looking at the approximate epsilon-Nash problem in this framework with some progress. So. Okay, and I think I have a few more minutes. Maybe I should make a few more comments. So this goes back, I guess, to one of the questions that I had earlier. So maybe the C-Epsilon property is not reasonable, but maybe an approximation of it is reasonable. And in fact, we did analyze a relaxation of this C-Epsilon property. And in particular, we analyzed one that allows for outliers. So for example, we say that the data satisfies a new C-Epsilon property if it satisfies the C-Epsilon property only after a number of outlier or misbehaved points, ill-behaved points have been removed. Right? So we say that the data satisfies the C-Epsilon property if a number of really bad points have been removed. Okay, and it turns out that, for example, in this case, we really need to output a list of clusterings, and we cannot output just a clustering. Now, if we think about it, for the C-Epsilon property, any two clusterings of a given data set that satisfy the property will be close to each other, will be order of epsilon close to each other. However, it turns out that for this new C-Epsilon property, two different sets of outliers could result in two very different clusterings satisfying this property, new C-Epsilon property. And this is true even if most of the points come from large target clusters. And so in this case, the best we can hope for is to output a small list of clusterings satisfying with the property that any clustering satisfies this new C-Epsilon property will be close to one of the clusterings in the list. So list clustering is here necessary. Okay, and so this is an example of a relaxation of the C-Epsilon property that we analyzed. And more generally, let me actually skip this example. I guess more generally, going back to the general picture, one could imagine going back to this more general picture where our goal was to get a clustering of low error, one could just imagine analyzing other types of properties about how the target clustering and the similarity measure relate, and develop algorithms that can be used to cluster well if those assumptions are satisfied. And in fact, I have a whole line of work that does this. And the interesting fact is that, for example, so the C-Epsilon property was an example of a property where we are able to output just a single clustering that is close to the target clustering. However, it turns out that once you start analyzing more interesting properties, more realistic properties, basically it's not possible to just output a single clustering that is close to the target clustering. And what we did, we were looking at clustering well up to a tree or up to a list. And I think that actually this is a really interesting direction to analyze.
What do you mean
up to a tree? Good. So what I mean is to output a tree such that the target clustering is close to a pruning of the tree. So let me give you an example. Okay, so here is a different. Okay, so now I'm going back. I'm going away from the C-Epsilon property. And let's just consider another property, a natural property that you might hope that your target clustering is going to satisfy with respect to your similarity information. So let's assume that you have the following property that says that all points, it sounds very strong, all points are more similar to points in the wrong cluster than to points in any other cluster. So we are given a similarity information that satisfies this property. Yes, so this sounds extremely strong, really strong. All points are more similar to points in the wrong cluster than to points in any other cluster. However, it turns out that in this case, you don't have enough information to just output a clustering that is close to your target clustering. Why? Because you could have multiple different clusterings of the same data that satisfy this property. And since you have no labeled examples, it will be impossible for you to know which of them is your target clustering. And here, I have an example here. So say that you have these 4 blobs over here. The similarity between each of the blobs is 1. The similarity top down is 1/2, and the similarity across is 0. Now, if you think about it, even if I tell that the number of clusters is exactly 3, then we still have 2 clusterings, particularly this one here and this one here, that satisfy this property. They both satisfy the property that each point is more similar to points in its own cluster than to points in any other cluster.
One answer would be that in this case, the assumption that there's 3 clusters is false, and there are really 4 clusters, and we should output the common refinement of all these clustering to satisfy the process.
Well, this would be
Breaking the rules.
This would be one way to solve the problem, but a different way to solve the problem is to, well, actually, no. My target clustering, to be honest, is maybe this one. I mean, I'm the user, and this is my target clustering. And this is what I want to see as an output.
This comes back to my understanding of the kid's original question. And if this target clustering is a virtual sense of a subjective idea, so the advantage of the k-means or cluster is to say we have some objective definition of what is a good clustering. But here the notion of target clustering, which it's not clear how is that.
Well, but usually in supervised learning, we have the notion of a target function. And you use the input, like in supervised learning, right? We have a notion of a target function, we use labeled examples, and we learn it, right? Similarly here, we have a notion of a target clustering. We use the similarity information that we are given, and we want to output something, that is close to our target clustering. And, right, these examples...
I think where this notion comes from.
I mean, the true clustering of proteins by function, for example. It's a target clustering, right? It's just that, so for example, for clustering protein sequences by function, there's a true clustering of protein sequences by function. In that case, that's a simpler case. Now here, it's a true, so my...
Someone gives you that, how do you tell that this is the true one and not?
So the assumption is that the user would know to recognize it, right? So I would be able to, if you're...
the user, when he knows, he applies some criteria, some measure of distance. So then if you go, his knowledge is not some abstract thing. There is some way the knowledge of the user tells this is a good cluster.
You get feedback in different forms. You can get feedback in the form of you show them a sample cluster and ask them if this is a good cluster or not. Or you can give them pairs and ask them, should this be the same cluster or not? So there's multiple ways you can elicit feedback from users and then use
but that should be part of the model. For instance, in supervised learning, there is a target function, but you can see the function in action. You can see what the function does on your sample points.
Yes, similarly here, I can see what it does, so I can see the partition, right?
No, I mean, if you can't see your target clustering in action. If I give you something, I don't know whether it's close to target clustering or not. I never see it in action.
What do you mean by that?
I cannot verify it. What is the equivalent of, in supervised learning, there's a target function, but I see the function being acted on the sample points.
Okay.
So there's no equivalent of that here. I can see what this function does on my sample.
Well, I can see the label of every single, right, so I can similarly we can do exactly what he said. For example, say, I can verify, so maybe I can take a few points at random from the whole set of documents, and so maybe the algorithm presents me all topics as a proposed cluster. I can draw a few points at random, and then I can ask the user, is this really a true cluster? And then the answer might be no. In that case, what my algorithm would do would then split into 2, and then you get a few points at random from fashion, and then you verify that those points are in the same cluster or not. So you can just
So what I'm saying is that is not part of the model.
Well, it
this
is.
Thing that you're saying, you can show it to the customer and ask him if it is the right.
No, it's an assumption. We assume no. It's an assumption. It's an assumption that there is a hidden target clustering, and somebody knowing the ground truth labels can measure closeness to it. The algorithm cannot measure closeness to it, but the user can verify closeness to it.
This part is not part of
it. It is implicitly. It is. It's just that the algorithm cannot use the labels, cannot use the ground truth label. But once you deploy, for example, like here, a tree, and once you propose a clustering, the user can verify closeness to it. I mean, that's implicit an assumption.
I think that the root cause of this discussion is the problem of clustering is opposed.
Well, well, the problem of clustering is ill posed. What I try to do in my work is to make it well posed. And actually, one way to think about this, like analyzing these properties, is in a way trying to make it well posed. And in fact, the way I think about a property, so for example, this is an example of a property. So the way I think about one of these property, or the C-Epsilon property, it's really the analog of a concept class in supervised learning, right? It captures the bias, our prior knowledge about the clustering problem, right? In supervised learning, if you assume that the target function is a linear separator, you're going to use a linear separator learning algorithm. If you assume it's a decision tree, you're going to use a decision tree learning algorithm. And similarly here, depending on what's my assumption, what's my prior knowledge about how the similarity function relates to the target clustering, I'm going to use a certain clustering algorithm versus another. I mean, the only interesting fact that comes in the context of clustering is that since we have no labeled examples at all, when you analyze more realistic properties, you really want to output a difference, not only a clustering, but maybe a different structure, maybe say a tree that compactly represents many different clusterings that could satisfy the property.
But there is the result of Kleinberg who showed that if you try to make certain actions.
So he makes us axioms about the clustering algorithm, which is a bit different.
Yes. It's true, but he was trying, and you've taken a different view on that, but he was trying to say, and this is what we see here, that if you make certain assumption of what you can expect to happen, so things like, if I just blow up everything, I don't expect my cluster to change and stuff like that, and if you make this kind of assumption, still you can come up with different solution which all satisfies your assumptions. So, and that's the reason why here we cannot...
the case is not fixed.
Sorry?
In this case, one of his assumptions that the number of clusters is not fixed.
No, in the more general model,
yes, these assumptions are questionable. It's not. I don't think that it's a done deal, right? But still, I think that the example that we see here is exactly this type of assumption where
Right. So even in Kleinberg's case, so he forces the algorithm. First of all, the way his approach is a bit different. He comes up with axioms, so not are reasonable clustering algorithms, which, as you say, are questionable. But he forces the algorithm to output a partition. Even in his case, if you allow the algorithm to output a hierarchy or something more, then these axioms will break. So, yeah. And by the way, for this more general model case, not fixed. It was just for the C-Epsilon property, which was a specific part of my talk. Yeah.
Yes. Most NP reductions start with extremely bad problems that the clustering can barely be made to work. And now they're relevant to this stuff where it's cases of clustering does make sense.
Right, so one way to interpret this work, so there are, thank you, that's a good point. So there are, two ways to interpret this work. So the C-Epsilon property, going back to the first part of the talk. So one way to interpret it is, well, we make an implicit assumption that explicit. So this is one way to interpret. We make an assumption about how the target function, the target clustering relates with closeness, with the similarity information that we are given. So this is one way to interpret it. A different way to interpret it is that we show that we can cluster well if some natural assumptions, natural stability assumptions are satisfied. And in particular, the stability assumption is that any two clusterings that have a good, say, k-median value are close to each other. Right, and in that case, we show that you can cluster well. You can. Yeah, so that's a very good point, actually. All right, more questions?
Sort of a broad high-level question, I guess. So in supervised learning, you have labels.
Yeah.
Like you said, you're trying to come up with a function that gives you the label given a data point. And like in both supervised and unsupervised learning, you have to make an assumption with your model. Like, you could use like a median. You could use the same model as a median in supervised learning. You could just say like you're going to calculate the size of the cluster given the labels. Like,
yeah.
So it seems you can use the same models in supervised and unsupervised settings. Like when you get.
So in supervised, you have a lot more. So the algorithm has a lot more power because you can get labeled examples, and moreover, you can test. So when I do some calculation and come up with a hypothesis, and then I can test it. While in the clustering case, the problem is somehow significantly more difficult because.
Yeah, I guess if you have in the unsupervised case, if you have the right model.
Yeah.
So like in this case, it's like I guess it seems the C-Epsilon assumption is basically that you have the right model for the data, like that the data is separable in whatever feature space.
Right, so these are assumptions. Right? The C-Epsilon assumption is an assumption. This would be a different assumption, right? And
if you have the right model, then is the unsupervised case sort of like is it at a disadvantage? Like is it going to get confused? Like is the unsupervised case more likely to, say, split a cluster that should be combined as the supervised case? Is it more likely to make those kind of mistakes? I mean, other than the fact that you can't get the actual label, like, if you have the right model, is it more likely to split clusters or join clusters that should be distinct? I don't know if I'm...
Well, you need to be a bit more specific, right? I mean, so having labels, like even for supervised learning, you can use a similarity information in addition to labels, and you already have much more power, right? Yeah. Like learning with kernel functions, similarity functions have similarity functions plus labels. I mean, already the labels give you a lot more power, right? Because the algorithm can use a label to check, if it does some computations, it comes up with some hypothesis, and then it can check, is this close to being something good or not? But for clustering, you cannot really do that, because the only information you have is the similarity information. And so, I mean, there is a clear advantage in that sense.
Yeah, so I guess in the supervised case, you definitely would not make the kind of mistakes like that an unsupervised.
Right, so like maybe split a cluster when they should have been together, for example.
Yeah, okay.
Yeah.
So Nina will be here till Monday, and feel free to get hold of her and discuss. So let's thank Nina.